Hi everyone. So today we're going to start on 4.1. It would be our first chapter in differential calculus. So we're actually going to talk about some of the things that you might remember learning in BC calculus. So hopefully it will make it more familiar to you. So before we get started, let's what we're going to first try to do is try to talk about what we call classification of functions. The reason why is because we kind of need to know, and you probably remember me saying this all the time, is that you kind of have to understand what type of function that we're working with. In this case, meaning like what dimensions are we working with, in order to know what you try to do. So when we get to calculus, and when we try to talk about derivatives and integration, it is also extremely important that you pay attention to what dimension you're working with and what type of function you're working with, because it actually changes the definition of the derivative for us. So we call the following. We call a function is a relation where every input has a unique output. Okay, a relation is nothing more than just a way to relate two things together, and the two things that we relate together, one of them is called the input, the other one is called the output. And a function is a special kind of relationship where every input has only a unique output come out of it. It cannot have two different output per input. That's not allowed. Okay. However, multiple input can give the same output, which is okay. Okay, but you just cannot have one input give multiple output. That's not allowed to do. Now, you also probably remember these two terms. The set of all the input is called the domain. And the set of all possible output is called the range. Now, here's the interesting thing is that the set of all output, I mean those actually come out from the function, is actually referred to as the image of the function. So what does that mean is the following. So when we write a function, you probably see me define a function this way before. I'm going to say f, and then the colon, and then d to r. So here, the d basically stands for the domain. All possible input, everything that we allow to plug into the function is all collected together into this thing called the domain. Okay, and of course the f is basically the name of the function. So we choose to call this function f because the word function starts with the letter f, of course. And then r is basically stand for the ring. And then what happened to image? So here, if you think about it, think about like here is the set of all the domain. If I pick one single input right here, let's say this is an input. It doesn't matter what the input is. Then here is the range, and that input will now connect it to an output through the function f. Okay, so that's how the association works. So anything you plug into the function have to be inside this d, and anything that pop out must be inside the r. So now where's the image come in? So the image would be this. The image will be the following. If you take the entire domain, and then here's the entire range, and you take the entire domain and map into the image, the range, then you have this group that all the output that actually reside, and that's called image. Now, as the picture suggests, the image should be inside R and should be somewhat smaller than R, and you will kind of correct. The image can be as big as R, but cannot be bigger. Okay, because R consists of everything that could potentially come out from D, from the function f, while the image is actually those that get used. Okay, a very simple example with the following. So example, suppose I take a function and then map from R2 to R3. That basic statement basically states that this function take in any vector in R2 and then the output will be a vector in R3. But does it actually give out every single possible vector in R3? The answer might be no. Okay, because it depends on what the function does. Okay, and I'll explain to you how that works with some more concrete example as we get through chapter 4. Chapter 4 kind of lay the foundation of how we deal with different type of functions, and then we'll go talk about how do we deal with the derivative of those functions. So it's going to be, slowly developed into the concept. Now that we know what domain and range and also image are referred to, now the next thing I want to talk to you about is the following. So last year in BC Calculus, the function that you study, so all the function you have learned or you have encountered have only one single independent variable, which is usually referred to as x, and only one single dependent variable. Oops. Which is y. Such as the function that you learn is y equal to f of x. Okay, so in this expression right here, also very easy to understand, the y is defined to be the dependent variable because it's understood that what you get for y is dependent on what you plug in for x. F here is the name of the function. And then x here is our independent variable. Alright, good. So in this case, our function f would actually be defined to be f mapped from R1 to R1. So meaning that this function take in a single real numbers and they pop out a single real numbers. In this case, this function both input and output are scalars. Now here comes something interesting. So this function actually mapped from R to R. Now give you an example, that way I can try to identify or show you what's happening with domain, range, and image. So imagine I have this function. Imagine the function f of x equal to x squared. So everyone know what the function look like. So here's my x, here's my y, and here's what the function f of x equal to x squared look like. It's a very simple parabola. Okay, so now let's talk about how this function is defined. So we define this function to be f mapped from R to R. Because it requires one single real numbers, and in this case our domain is negative infinity, positive infinity, meaning any real numbers. And it maps into any real number. Now, but here think about the following. So this indicates that our domain of the function is all real numbers. And our range is R also, which means all real numbers. But of course, this statement basically stating that if I plug a real number into function f, I can never get something that's not a real numbers from it. But if you look at the graph, or if you simply think about the function x squared, some of you probably remember that the range is not all real numbers. You probably remember learning that the range is all positive real number and 0 non-negative real numbers. And that is true. The problem is that it's actually incorrect to call that the range. That is actually properly referred to as the image. The image is everything that's greater than or equal to 0. Non-negative real numbers. And if you think about it, it makes sense that the image is actually smaller than the range because only part of the range is being used as the actual output of the function. So that was always a confusing terminology, especially because of the algebra 2 would choose to use our range as the word image, but that is incorrect. So now that you should know the distinction between them. The image is what the actual output of the function is, while the range simply loosely define what the output should be. Like in this case, it's simply loosely defined that the output must be a real number. But what kind of real number? Well, it didn't specify. It just have to be real numbers. And then when we look at the actual function itself, realize that the actual output is not just a real number, but also actually non-negative real numbers. Now, this little function has a name. Okay, so this little function is called a real value function of a single variable. Okay, and the reason I call real value function of a single variable because the following: the real value indicate that the range is R, and the single variable indicate that our domain is R. So therefore, when I say a function is a real value function of a single variable, that means you have a function that maps from R to R. So now, what if you don't have a real value function of a single variable? What other type of functions are there? So this is how it works. This is how a classification works. If a function has more than one independent variable, then it is called a function of several variables, which makes sense because they have more than one independent variable. Function of several variables. If a function has more than one dependent variable, then it is called a vector value function. Now, how does it compare to our real value function single variable? So notice that when I say more than one independent variable, that indicate the domain is not R1, but maybe Rn. And when I say more than one dependent variable, we're kind of saying that the range is Rm. So now we can now classify all function into 4 different categories. So now we can actually classify our function into 4 different categories. So therefore, we can now classify all functions that we're going to be dealing with into the following 4 types. So what is 4 types? The first one, which is what you learned last year, a function f that map from R to R. So this type of function is called a real valued function of a single variable. Which is the reason why last year when you're in BC calculus, what you learned is called single variable calculus, because of the fact that you have one single independent variable, but also kind of saying that the dependent variable is also single. So these sort of function will look something like this: y equal to f of x. That's basically how it looks like. Pretty simple. That's what you have learned probably since the first time you get introduced into a function notation, which would probably be like, I don't know, 7th, 8th grade maybe, 9th grade maybe. So I don't know when you actually learn function notation, but that would be what it is. Now, what we're going to talk about this year, obviously, would be multivariable calculus. So how does that work as multivariable calculus? The way it works with multivariable calculus is that we're going to try to talk about functions that have either multiple independent variable or multiple dependent variable or multiple independent and dependent variable. So let's talk about the 3 remaining type, and we actually going to go through these 3 types in the following order. The first we're going to do is we're going to try to figure out what happens if we still have one single variable, but the output has multiple dependent variable. That would mean that we're looking at functions that look like this. So that would actually be the focus of what we're going to talk about in 4.1. Okay, function like this, where we call the vector values function of a single variable. It's vector value because the output of the function is actually a vector in Rm. That's the reason. So therefore, this function will look something like this. It will be f of x equal to vector y instead of y. Because if you just say y, that will be a scalar. So a single value or real value. But now you put arrows on top. Now that indicates that we have a vector. A vector y. And in this case, vector y is actually in Rm. Alright. Number 3. Oops. Then we're going to talk about this type of function. What if we have multiple independent variable, but it's still mapped to just one single value? So this is a real valued function of several variables. So we're going to deal with what happens if we have multiple independent variable, but yet the output still pop out to be one single number. Now, you might be thinking like, that's kind of weird. Why would a function do that? Well, it shouldn't be, because you already know how to something similar to that. Think about dot products. It kind of combines vectors into a scalar. This is exactly how they work. You basically take an input of vector and then pop out some kind of single number out of it. Okay? This function will look something like this. We'll say y equal to f of vector x. Now the input is now a vector. And as a matter of fact, x is a vector in Rn. And then finally, toward the end of chapter 5, we'll finally talk about these type of function. What if you have several independent variable and several dependent variable? This is called vector valued functions of several variables. And this function looks something like this. Vector y equal to f of vector x. Oops. So these are the 4 different type of functions that that we can define. So now the important thing is that what we're going to do for the rest of this school year is to talk about integral and differential and derivative of these 4 type of functions. Okay, and you already know how first type is going to work, because the first type of function is what you basically learn in AP Calculus BC. That's basically what you learn in the first type, which is the reason why when you learn about AP Calculus BC, you are technically learning what we call single variable calculus. Because of that, it's single independent variable, single dependent variable. Okay. We will be talking about type 2 and type 3 mainly in chapter 4 to try gaining understanding of these type 2 type of function. But we'll actually talk a little bit more about type 3 in the beginning of chapter 5, and we'll finish chapter 5 by talking about type 4. So we're actually going to work through kind of like from 1 to 2 to 3 to 4, starting from last year BC Calculus you learn about 1, chapter 4 we learn about 2, end of chapter 4 and beginning of chapter 5 we talk about 3, end of chapter 5 we talk about type 4. Alright? Now, in order to properly understand how the derivative and even integral work with these remaining 3 type of functions, I'm going to have to introduce something important first. So next thing I want to talk to you about is this. Next thing I want to talk to you about is a concept called coordinate function. All right, so what are coordinate functions? So in general, a vector value function is defined by a set of what we call coordinate functions. Each coordinate function is a real value function. The reason why it's a real values function, because it's a real value function that defines one single coordinate in the output of the vector value functions. So how does that work? So first of all, make sure you understand that a coordinate function is a real values function because it's designed to only give out one single coordinate within a vector, which is the output of a vector value function. It cannot give out multiple coordinates, so therefore it cannot give out a vector in return. So how does that work? So show you how that works. Let's say we define a function f that maps from Rn to Rm. Okay, so in this case, let's say we define vector x to be the input, and since vector x is in Rn, I'm going to say vector x is x1, x2, ... to xn. Now then imagine what is the output going to look like. So if you think about it, let's say f of vector x is equal to vector y. Okay, so therefore imply that our output y must be y1, y2, ... to ym. Notice that the output of the function f is in Rm, so therefore must be a vector in Rm. Now then think about the following. In this scenario, meaning that when you plug something into function f, a function f must return m different numbers. The first number being y1, the second number being y2, and then so on and so forth until the last number, which is ym. So each of these numbers must be defined by its own individual function, and those functions are what we call coordinate function. So in this case, interesting to identify is the following. In this case, we'll define that y1 must be some kind of function f1 of vector x, and y2 must be some function f2 of vector x, and so on and so forth until ym must be some function f of m of vector x. Collectively, we know that f sub k must be a function that maps from Rn to R. And what does it do is, and it gives the k coordinates in the output vector y. Now, it might sound very confusing, but once I show an example, you'll be able to see how that works. It's actually a very simple concept. So imagine the following. Imagine I have a function f that maps from R2 to R3. So what does that mean? Meaning that the function requires to plug in a vector in R2, meaning two variables, but it pops out three different output. Okay, so here I'm going to define the following. I'm going to go and let f of uv equal to x, y, z. So therefore, we basically identify this is a vector in R2, and this is a vector, x, y, z is a vector in R3. Now, also important to notice that in this scenario right here, I'm defining u and v are being our independent variable. Oops. And x, y, z are our dependent variables. All right. Now, so that doesn't really help much. So how about we actually put a function into this? So let's say function is defined to be following. Let's say, let's define f to be the following. F of uv is equal to uv cosine u. So notice that when I define this function f, I have to define three separate formulas because I need three separate output for it to be a function in R, map into R3, or the range should be in R3. So in this scenario right here, I can now identify that this function right here is our f sub 1 of uv, which is just equal to u. This middle one is our f sub 2 of uv, which is just u times v together. And then this last one right here is what we call f sub 3 of uv, and that will be cosine u. So therefore, f sub 1 right here is technically speaking called the first coordinate function. Why is it called the first coordinate function? It defines the first coordinate in the output. And then this, f sub 2, is our second coordinate function, because it defines our second coordinate. And then you can guess what f sub 3 is. F sub 3 is called the third coordinate function, because it defines the third coordinate. And of course, if you have a function that have map into R12, for instance, then you have 12 different coordinate functions. Each one define one single coordinate within the vector R12. Now, interesting thing to note is that it's not wrong for you to write this. It's not wrong for you to call f sub 1 of uv x of uv. And then f sub 2 of uv to call that y of uv. And then f sub 3 of uv to be z of uv. So that's not wrong to say that, which is perfectly okay. The only problem obviously is that when I use x, y, and z, then I'm kind of working in R3, but if in higher dimension, then we're going to have to use forced to be using subscripts. Okay? Good so far? So unfortunately my time right now is already 31 minutes, so I'm going to stop right here for today, and we'll continue some more tomorrow. Alright? Okay, talk to you guys soon. Bye-bye.